Ladies and gentlemen, welcome back to yet another installment of Hansen Math videos. Today's video regards Pascal's triangle and some applications of it. What you see in front of you is called Pascal's triangle. It consists of rows and columns, all starting with 1. And what we're going to do first is I'm going to show you a little bit how you can generate it from scratch. You start with a 1. And then to either side of that, you have 1s. Okay? This is row 0. This is row 1. To generate row 2, what you would do is the following. You'd start with a 1. You'd add this guy and this guy. 1 plus 1 is 2. And then you end with a 1. Okay, so this is row 0, row 1, row 2. To get row 3, you start with a 1, you add these guys together. 1 and 2 is 3, that goes in the middle. 2 plus 1 is 3, that goes between these two, and then you end with a 1. There's always one more number or element than the row number. So again, note in row 2 you have 3 numbers, and in row 3 you have 4 numbers. You can guess in row 4 you're going to have 5 numbers. You start with 1, you add these first two together from the previous row, so 1 and 3 is 4, 3 and 3 is 6, that goes in between, 3 and 1 is 4, and then you end with a 1. Okay, you can keep generating Pascal's triangle by using the same format. Okay, if I want to do row 5 real quick, I'd slap down a 1, I'd go 1 and 4 is 5, 4 and 6 is 10, 6 and 4 is 10, 4 and 1 is 5, and then end with 1. You'll notice there's symmetry involved here. If you draw a line of symmetry like right here, basically the odd number rows are the same forward and backwards. You have 1, 5, 10, 10, 5, 1. They kind of split in half. On the even number rows, you do have a definite middle number, so you have 1, 4, 6 is in the middle, and then you go in reverse 4, 1. Again, you could keep generating this as long as you would like to. Okay, next. How do you read Pascal's triangle? Well, I already alluded to that. We'll go through it again real quick. This is row 0, row 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Now, it does keep going forever. I ran out of room, of course. Here's one way you can look at this. The row number is distinguished not by looking at the first one, because these are all ones. Okay, that doesn't really do anything. You'll notice in row 2, 2 is the first non-1 digit. In row 3, 3 is the first non-1. In row 4, 4 is the first non-1. So if someone tells you to look for row 7, your eyes are going to be attracted here. Okay, again, you disregard the first one. Row 7 starts with a 7 after the 1. Row 8 starts with 8 after the 1. So on and so forth. Also, you would say column-wise, like if we look at row 4, this is element 0, this is element 1, this is 2, this is position 3, this is position 4. Okay? That's how you read Pascal's triangle. We will practice this a little bit more as we go. Okay, we'll move on to some concrete examples of how and why this is used. Alright, first we're going to try a very basic binomial expansion. You've probably done this one before or ones like it. And we'll see how Pascal's triangle relates. Pascal's triangle, to kind of jump ahead here, it's used for binomial expansion. A binomial is a two-term polynomial. So in parentheses here I have an x and a y. Those are our two terms, hence that's why it's a binomial. Bi means two. Now, we can raise this binomial to any power we like. I'm going to start by raising it to the second power. The second power is your squared power, which means anything times itself. So in essence here, what we're really looking at is x plus y times itself, x plus y. Now, this is multiplying, or the distributive property, but for a binomial to the second power, you're really using the FOIL method. So if we multiply the first terms in each parenthesis, x times x is x squared. The outside, you have x times y is xy. The inside is y times x, which is xy again. And the last is y times y, which is y squared. Combining like terms, you have x squared. You have xy plus yet another xy, that's two of them, so it's plus 2xy, and then plus the y squared at the end. Now, note that x squared and y squared, there's only one of them, so you can put in the one if you like. It's usually invisible, it's implied, but we can put it in. So notice that we raised this binomial to the second power. That's row 2 in Pascal's triangle, which is this one right here. This is row 2. And look at our coefficients we ended up with. We have a 1, a 2, and a 1. And that's what Pascal's triangle gives you, 1, 2, 1. Okay, so as you're going to see, Pascal's triangle gives you the coefficients for binomial expansion. As we practice this more, you'll see how it works. Let's go on to a different power, and I think you'll better see the pattern. Okay, here again we have our simple binomial of x plus y, but this time we're taking it to the third power. So I'm going to write it out as the three multiplications, x plus y times x plus y times x plus y. Okay? We already saw from the previous example, when you multiply two of them together, such as these two, you end up with x squared plus 2xy plus y squared. Okay, if you don't believe that, you probably want to go back and look at the previous example. So this one and this one are done. They're multiplied through. So now we have to multiply this trinomial by the remaining binomial x plus y. To do this, we use the distributive property. So I'm going to start here with the x squared. X squared times this x is x cubed. 2xy times this x is 2x squared y. And y squared times this x is xy squared. This x just got distributed to bink, 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 everything, so now it's done. We do not need to multiply it anymore. Now we need to multiply the y term to everything over here. Bink, bink, bink. Here we go. X squared times y is x squared y. 2xy times y is, pardon me, let me make this a little bit clearer, that's a plus. It's 2xy squared, and y squared times y is y cubed. Okay? Now, what we're going to do here is we're going to see if we have any like terms to combine. And down yonder we have 1x squared y. That's a total of 3x squared y. Here we have an xy squared, and down further we have 2xy squared. That's a grand total of 3xy squared. And then we have the y cubed hanging out at the end, y cubed. Now, if you look at the coefficients, we have 1 of x cubed, 3 of x squared y, 3 of xy squared, and 1 of y cubed. So the coefficients are 1, 3, 3, 1. 1, 3, 3, 1. Since this was a third power expansion, we look for row 3, 0, 1, 2, 3. That's this one right here. 3 is the first non-1 entry, and the coefficients are 1, 3, 3, 1, just like we get here. 1, 3, 3, 1. Now, you might say this is silly, but it's very, very helpful when you get into something much more difficult, like raising something to the 5th power. Okay? I would have to write this out 5 times and multiply it through. That's going to be quite the fiasco. I don't want to do that, so I'm going to show you the shortcut. What you need to do is look at Pascal's triangle. You can flash back to the previous slides at the beginning where I show Pascal's triangle. Basically, you need to find row 5. That one starts with 1 and 5. I'm going to write out the coefficients and kind of spread them out. So we have a 1, we have a 5, we have 10, 10, 5, and then 1. Okay, so that's step 1. You write out the coefficients. Now, the next thing I do is I take the 2 components of the binomial. In this case, we have x and we have positive 6. So after each coefficient, I'm going to write out the x and the positive 6. After the 5 coefficient, x, positive 6. After the 10, same thing. All we're doing is after the coefficient, we're writing out the terms of the binomial. Okay, I'm sorry here, that's getting a little bit crowded. Okay, now how this works is as follows. The power we're raising this binomial to is the 5th power. So the x here gets the full 5, and then the 6 gets raised to the power of 0. So you start with the full boat power, 5, and then the 6 gets 0. These two together have to add up to this power here. If they do not, you made a mistake. And then following the pattern, it descends. So if we start with 5, now x goes down to the 4th, but the 6 goes to the 1st. Again, these two have to add up to 5 if that is our power we're raising to. So then we go down to 3 and 2, 2 and 3, because it's got to add up to 5, 1 and 4, and then 0 and 5. Okay, so it goes 5, 4, 3, 2, 1, 0. And then the second term of the binomial goes ascending. 0, 1, 2, 3, 4, 5. Okay, so what we're going to do is the following here. We're going to multiply this out, or expand the powers, if you will. This coefficient of 1 doesn't really do anything, so we have x to the 5th, which is x to the 5th, and 6 to the 0 power is 1. Multiplying by 1 doesn't do anything. Now, over here we have 5. We have x to the 4th, which is just that, and we have 6 to the 1st power. 6 to the 1st power is 6. So we have to multiply by a 6. Okay, we'll take care of that at the end. Now, we have 10 here. We have x to the 3rd. And we have 6 squared, which is 36. Here we have 10. We have x squared. And we have 6 to the 3rd power. Let's see, 6 to the 3rd power is 6 times 6 is 36, times another 6, 216. Here we have a 5, we have x to the 1st, and we have 6 to the 4th, which is 1, 2, 9, 6. And then finally we have a 1, we have x to the 0, which is still 1, and we have 6 to the 5th, which is 7776. 7776. Okay. Cleaning this up a little bit, we will get our final answer. We have x to the 5th. We have a 5 times a 6 down further, which is 30, x to the 4th. Here we have a 10 times a 36, that's 360 x cubed. We have a 10 here times a 216, that's 2160 x squared. Let's see, we have 5x times 1296, so that's 1296 times 5 is 6480x plus our last constant here, which is 7776. Now, you might think this is a lot of work, and I'm not here to argue, but I can tell you this much. This is a lot quicker than if you were to have written x plus 6 out and multiplied it 5 times. The likelihood of making a mistake is much more grave. Okay, if you practice this a few times, it will work out. Again, go back through the instructions. First, you write down the coefficients given by the power. That tells you which row to look at. Then you slap down your elements. You want to look for the row that starts with 1, 4, since it's the 4th power. So the row with 1, 4 has coefficients of 1, 4, 6, 4, 1. Okay? That's step 1. Write down your Pascal coefficients. Step 2 is after each of those coefficients, you write down the terms of the binomial, and I like to use parentheses. So here we have a 2x and a negative 3y. Okay? Now we have a 4. That has to get multiplied by 2x and negative 3y. The 6 also gets multiplied by 2x and negative 3y. Same with the 4. It gets multiplied by 2x and negative 3y. And finally, the 1 down here gets multiplied by 2x and negative 3y. Okay. Now, to apply the powers, you start with the full boat of 4. So on this first term, 2x, it goes to the 4th power. The next 2x goes down to the 3rd, you descend. The next 2x goes to the 2nd, the next 2x to the 1st, and the last 2x to the 0 power. Since every piece here has to add up to the degree of 4, if we use 4 here, we're forced to use 0 here. If we have 3, this has to be 1. Get it? Because they have to add up to 4. The powers of the second term ascend. So it starts with 0, and then 1, and then 2, and then 3, and then the full boat of 4. Okay? Now we'll start crunching this guy out. We have 1, which multiplying by 1 doesn't do anything, so we have 2x to the 4th. Now, both of these get to the 4th power. That's where a lot of students make a mistake. So 2 to the 4th is 16, so we have 16, and x to the 4th, which is x to the 4th. Anything to the 0 power is 1, multiplying by 1 doesn't change anything. Okay, moving on. Now we have this coefficient here of 4, so we have that. And then we have 2x to the 3rd. Well, 2 to the 3rd is 8, and x to the 3rd is x to the 3rd. And then this negative 3y to the 1st, that just remains negative 3y. Okay? Next, we have a 6 times 2x squared. 2x quantity squared, forgive me, is 4x squared. And then negative 3y squared, well, that means negative 3y times itself, which is positive 9y squared. Okay? Keeping on trucking, here we have our 4. 2x to the 1st is still 2x. And negative 3y to the third, well, negative 3 to the third is negative 3 times negative 3 times negative 3. That's negative 27y to the third. And then finally, for the last term here, we have 1 times 2x to the 0, that's 1. And then we have negative 3y to the fourth. Well, a negative to a positive, a negative to an even power is going to be positive. So we have positive, let's see, 3 to the fourth, 3 squared is 9, and 9 again, that's going to be 81y to the fourth. Okay. All that's left to do is tidy this up a little bit. So let's bring down our 16x to the fourth. Over here we have some multiplying to do. We have a 4 times 8 times negative 3. 4 times, let's see, 4 times negative 3 is negative 12 times 8 is negative 96. And that is x to the third. And then here we have y. Let's see, plus we have a 6 times a 4 times a 9. 6 times 4 is 24, and 24 times 9 is 216. So we have 216. Let's see, we have x squared, y squared on that one. Now we have over here, we have 4 times 2 times a negative 27. 4 times 2 is 8. 8 times negative 27 is negative 216. So that's negative 216, and that was an x and then a y to the third power. And then we have plus 81y to the fourth. Okay, so there you have it. That's the expansion here of 2x minus 3y all raised to the power of 4. And notice that the signs alternate. We have a positive, negative, positive, negative, positive. And we also have some things going on here where, again, this term has the degree of 4. We have 3 and 1 here, which is 4. 2 and 2 is 4. 1 and 3 is 4. And 4. Okay? So there's your binomial expansion. You may have to view this again. I know it's a little bit tricky, but it does beat the alternative of doing it by hand. Okay, finally I want to talk about an application of Pascal's triangle to probability. If you have 5 items, say 5 candy bars, I'm just calling them A, B, C, D, E, very generic. Okay, 5 different things, A, B, C, D, E, and you want to choose any 2. You can arrange that 10 different combinations. You can put A with B, A with C, A with D, A with E, B with C, B with D, B with E, C with D, C with E, D with E. 10 combinations. Now, keeping in mind that reversing the order, we're considering the same thing because in a combination, order doesn't matter. For example, candy bar A and candy bar B would be the same thing as B and then A. We're just concerned with the grouping here, not the order. Okay, so in probability, this is called combinations. This is 5, choose 2. It means out of a pool of 5 things, how many different ways can you put 2 of them together? That's 10 combinations. Now, Pascal's triangle can help us do that a little bit more efficiently. If we go back to that example of 5, choose 2, and we know that the answer was 10 combinations, the 5 here tells us to look for row 5. Row 5 has a 5 after the 1, so we're here. And it says look for the second element. Okay, so this is 0, this is 1, this is 2. Hey, check it out. There's our answer of 10. If you wanted to do a different one, if you wanted to do like 8, choose 5, so you have 8 things, how many ways can you arrange it in groups of 5? We go down to row 8, which is this one, 1, 8, and then we'd go to the 5th element, so we go 0, 1, 2, 3, 4, 5. There would be 56 different combinations of choosing 5 out of a group of 8. thank you very much for working with Pascal's triangle. I hope you learned something new. And once again, I thank you for enjoying and appreciating Mr. Hansen's math videos.